Good morning. My name is Leigh Fletcher. I'm a planetary scientist at the University of Leicester, where I specialise in studying the atmospheres of the gas giants Jupiter, Saturn, Uranus and Neptune. Today I'm going to talk about the atmospheres of Jupiter and Saturn in particular and take you through some of the latest discoveries from missions like Cassini, that was in orbit around Saturn for 13 years, and the Juno spacecraft, which is presently in orbit around the gas giant Jupiter. What we're going to do is go through 7 individual sections for this particular lecture. I'll take you through the motivations for why we might like to study the atmospheres of the giant planets. I'll talk about how we've explored those worlds in the past via a combination of remote sensing and in situ measurements from visiting spacecraft, and also from observations from ground-based and space-based facilities, doing things remotely from an Earth-based vantage point. We'll talk then about the structure and circulation of these atmospheres and what we can learn about the physics of planetary atmospheres in general by looking at Jupiter and Saturn as an enormous planetary scale laboratory for understanding these perfect fluid dynamical flows. We'll talk about the presence of large-scale vortices like Jupiter's famous Great Red Spot and smaller scale plumes that arise from the deeper atmosphere and punch up through the overlying cloud decks to create spectacular features on the cloudy surfaces of these worlds. We'll then take a step back and look at longer term cycles than local meteorology. These are natural oscillations in the appearance of Jupiter and Saturn and what that might mean for what's controlling the atmospheres of these worlds. And then finally, we'll look to the future of exploration, how we're going to advance our topic and advance our scientific knowledge of these two worlds in the coming decade, and the kind of things that you may all hope to one day be involved in. So this is a scale diagram, scale impression of the sizes of the 4 giant planets and their collections of icy satellites. Now, I mentioned at the start that we can consider these worlds as being planetary scale laboratories for perfect fluid dynamical flows. And that's because if you think of the terrestrial atmospheres, Earth, Venus, and Mars, what you have there is a system where the weather patterns and the climate are being influenced by a connection to the surface of those worlds. So when you have continents and oceans and valleys and mountain ranges that get in the way of those perfect flows and cause jet streams and atmospheric circulation that is not all that easy to diagnose and understand. But when you take a step back and you remove those surface interactions, what you're left with is a big rotating sphere of fluid, and fluid in this case is gas when we look at the top of the atmospheres that we can see for the giant planets, but transitions as you go to higher and higher pressures into states of matter that we would consider to be exotic from the perspective of planet Earth. These are also time capsules for looking back at the origins of our solar system. These worlds are so massive that any material that was accreted within these planets back at the dawn of the solar system is still there today. It may be differentiated and mixed throughout the interior, but nevertheless, the elemental and isotopic composition of the 4 giant planets gives us a window onto what the conditions may have been like back 4.5 billion years ago when these worlds were first forming. Now, this presentation is going to deal with the planets themselves, but I want to remind you that these are hosts to a diverse collection of icy and rocky satellites, some of which may be potentially habitable. That is, that they have subsurface oceans of liquid water and the conditions may be right for life to exist on their surfaces or within their subsurfaces. And so exploration of the giant planets themselves doesn't just focus on the big gas balls in the center, but also looks outwards to these fantastic icy moons that are present in those systems, in addition to the rings and the large-scale magnetic field that encompasses and connects all of the diverse bodies within these systems. And finally, the 4 giant planets can be thought of as our template, our archetype, if you like, for understanding worlds of this scale that may be present around different stars out the extrasolar planetary systems. Now, unfortunately, given the great distances involved in reaching these giant planets, over the course of the space age, they've only been visited a handful of times. Jupiter has been explored by the Galileo orbiter and probe, by the Cassini flyby in 2000, and most recently by the Juno spacecraft, which we'll talk about at length in the coming slides. Saturn was explored via 13 years of remote sensing from the Cassini spacecraft, but the poor ice giants have been visited only once by a flyby spacecraft. That was Voyager 2 back in the late 1980s, and the ice giants will be subject of another lecture within this winter school. Now let's take a step back and look at a comparison between these two different groups of objects, the gas giants and the ice giants. Jupiter and Saturn can be thought of as being roughly 10 times the radius of Earth, whereas Uranus and Neptune are roughly 4 times the radius of Earth. So they're two different classes, or subclasses, if you like, within this type of astrophysical object. Now, Jupiter and Saturn formed relatively quickly in the early protosolar nebula and were able to accrete their surrounding material from that protosolar nebula at a time when there was still lots of hydrogen and helium remaining within the disk. What we see today are worlds that are completely dominated by hydrogen and helium, the lightest known elements and molecules in the universe. These are then combined with only very small traces of things like ammonia, things like water, things like hydrogen sulfide, and it's those very, very small traces of gases which give all the dramatic complexity that you see on Jupiter and Saturn today. But as you go down to great depths within the interiors of Jupiter and Saturn, the pressures and the temperatures rise to such tremendous amounts that hydrogen, that simple molecule of 2 protons, can actually take on a very exotic form that we call metallic hydrogen, where the electrons are stripped away from the protons and are able to flow through the interior, meaning that we have conducting metallic material down at great depth and at very high pressures. Now the connection between that deep interior and the observable atmosphere that we see is something that I'll touch upon later on, but it is exceptionally difficult to diagnose the conditions down there at great depths. Now, if we take a comparison and look at the ice giants Uranus and Neptune, as I mentioned, these are roughly 4 times Earth radii, and they formed more slowly within the protosolar nebula. In fact, they probably were forming at a time when some of those nebular hydrogen and helium gases were being lost as they were being ejected from our protoplanetary system. That means they just didn't have enough time to accrete all of that hydrogen and helium onto those forming protoplanets. This means that you don't have the dominance of hydrogen and helium within their composition. And in fact, it's things like methane, ammonia, water, and hydrogen and sulfide that dominate the composition and potentially form exotic slushes of icy material down at depths within the interior of the ice giants. That's very different from Jupiter and Saturn, which have the hydrogen and helium forming this metallic property down at great depth. So 2 different classes of worlds that we have there. But both of them really are best and closest representatives of what could be a common outcome of the planetary formation process out there around other stars, the pantheon of exoplanets that we've been discovering over the past couple of decades. Now more than 4,000 planets are known out there beyond our solar system. And actually, if you look at the census of planetary sizes that's represented in the diagram just here, what we see is that large-scale Jupiter and Saturn-like objects are actually quite small within the planetary census. And the same is true of Uranus and Neptune themselves. Terrestrial planets, we have an observational bias in terms of how many we have detected thus far, but it does seem to be that worlds that are intermediate in size between the rocky terrestrial worlds and the larger scale gaseous worlds seem to be the most common outcome. And it's this class called the sub-Neptunes down there at about 2.4 planetary radii, which seem to dominate the planetary census, and they maybe have the same conditions as to what we see on the larger gas giants Jupiter and Saturn and the smaller scale ice giants Uranus and Neptune. So our key motivation for studying the giant planets in our solar system is to understand the physical, chemical, and originating forces that led to the worlds that we see today as our template, our archetype for studying worlds beyond our solar system. Now let's look in a little bit more depth at how we're exploring these giant planets at the present time. If you look over the past 4 or 5 decades of planetary exploration, it all really started for the giant planets with the grand tour of the Voyager missions. Voyager 1 visited Jupiter and Saturn and then flew up out of the ecliptic plane. Voyager 2 did Jupiter and Saturn and then carried on going to Uranus and Neptune, and remains the only mission ever to have explored those 2 distant worlds. In the 1990s, the Galileo spacecraft was then launched from the space shuttle and arrived at Jupiter in 1995, depositing, still to this day, our only in situ probe at a giant planet, a probe that went down into the cloud decks of Jupiter to about 20 bars or so, lasting for about 90 minutes before we finally lost contact with it down below the cloud decks of Jupiter. But that's a treasure trove of information about the gaseous composition and the aerosol composition of Jupiter itself. Galileo continued to work, the orbiter, not the probe, continued to work until 2003, when it was deorbited into the Jovian atmosphere. And just 1 year later, the Cassini spacecraft finally arrived at the Saturn system after a 7-year journey and spent 13 years exploring Saturn. So the 2000s were really the era of Cassini. In the 2010s, we then had the Juno mission arriving at Jupiter in 2016, and we'll talk more about that in a moment. In the 2020s, we have the JUICE mission, the Jupiter Icy Moons Explorer, that will be launching to explore Jupiter, Europa, Ganymede, and Callisto at the end of this decade. And maybe in the 2030s, we'll finally have a new mission heading out towards the distant ice giants. Now, all of these visiting spacecraft are then supported and supplemented by ground-based facilities. And I've got a couple of photographs here, the lower photograph showing the collection of observatories out in Hawaii, the upper photograph showing the very large telescope out in Chile. And these provide long-term, high-resolution, high spectroscopic resolution observations of the giants that allow us to fill in the gaps between these short-lived spacecraft missions. Now, Cassini took 7 years to get out to the Saturn system, arriving in 2004, where it was originally planned to only have a 4-year mission. But that mission was so successful that it kept being extended and extended and extended. And it finally came to an end in 2017 as Cassini was running short on fumes, and it was deorbited into the Saturnian atmosphere in September of that year. Now, that long time span of 13 years means it was exploring Saturn for nearly half a Saturnian year. Saturn takes nearly 30 Earth years to go around the sun. So it was able to observe the various seasons on the gas giant and see how the atmosphere responded to changes in solar insolation. So how the chemistry changed, how the temperatures changed, and how the atmospheric circulation and dynamics responded to those different energy inputs. And this image that you see in front of you is a fantastic picture that shows the blue northern hues of Saturn when it was emerging from the darkness of polar winter, but before the chemistry influenced the atmosphere sufficiently to create the aerosols that you might be familiar with, which produce that beautiful yellow ochre appearance that we know of when looking through a telescope at Saturn. Now, Cassini's vantage point also allowed us to look at the poles of Saturn for the first time, to really scrutinize the dynamics that were taking place there. And we were able to observe a bizarre 6-sided hexagonal feature around the North Pole, many thousands of kilometers wide, that we know had been present at the time of the Voyager missions back in the 1980s, but we were able to characterize in great depth using Cassini's suite of remote sensing instruments. Right in the center of that polar hexagon is a swirling vortex, a cyclone, where air appears to be sinking down into the depths of Saturn and creating some fascinating dynamics as it goes. It's almost, consider it like a plug hole at the North Pole of Saturn, where air is sinking over that particular region, and a similar one is present at the South Pole. So Cassini did marvelous observations of the planet Saturn, and we'll get back to some of its discoveries later on. At the same time as Cassini was coming to an end, the Juno mission was just getting started in earnest. And Juno is on a big elliptical polar orbit, meaning that it screams close to Jupiter once every 53 days or so, capturing some of the closest ever observations of a giant planet that we've ever been able to acquire. Now, those close passes are known as perigeos, and those perigeos last for a couple of hours or so, during which a suite of remote sensing instruments are exploring the atmosphere, probing the interior, and also sampling the powerful magnetic field of Jupiter. And here's a montage of the various images that you get as you are screaming past 4,000 kilometers above the cloud decks, encountering the various storm features and banded features of the planet in a way that we never have before. And in fact, no spacecraft has really given us glimpses of the Jovian poles before. And you can see in these enhanced color images that they have a very different appearance, with little flecks of dynamic activity compared to the more familiar banded structure that you might see at lower latitudes. Now, Juno has delivered some stunning observations. I'm just going to share a couple with you right now. This is a field of filamentary turbulent regions with clouds that are popping up above the underlying cloud deck and actually casting shadows back across the deeper clouds. You can see fluffy white features that might be similar to cumulonimbus clouds on Earth, where you get powerful convection lifting material up to great heights. And we aren't even close to beginning to understand all the complexity in images like this. Down in the southern hemisphere, there's a large cyclonic structure that's been observed here that they refer to as the spectre, because its appearance can sometimes be very, very difficult to distinguish from the background. But again, Juno is so powerful in terms of its resolution that you can see all these individual cloud features that are still several hundred kilometers in scale, but in a way and with a resolution that we've never been able to accomplish before. We can stare down into individual anticyclones and cyclones, as we do on the top left. We can recreate what Juno might be able to see with a fisheye lens. This is some great processing by a talented amateur astronomer, Kevin Gill, who was able to capture this image montage of large white anticyclones. And up there in the top right is this great swirling great red spot that we'll come back to in a bit. In ultraviolet light, Juno is able to monitor and to sample the influence of the northern and southern lights, the aurora on Jupiter, as you have electrons from the magnetic field interacting with the gases within the planet's atmosphere to create swirling patterns that are changing on timescales of minutes and hours, that are depositing energy and influencing chemistry and aerosols within the upper atmospheres of these planets. And then finally, if we look in infrared light and look at the poles of Jupiter, we start to see patterns that we never expected would be present in the Jovian atmosphere. This is the North Pole of Jupiter, and you can see a chain of 8 cyclones swirling around a central cyclone, and that chain of 8 forms a kind of octagonal pattern around the North Pole of Jupiter. This is all within about 5 degrees of latitude of the North Pole. These things have been likened to vortex crystals that you were able to obtain in 2-dimensional fluid dynamics. But again, we are still only scratching the surface of understanding why these features appear to be there. And over the course of the last 4.5 years of the Juno mission, this polar arrangement of cyclones seems to be relatively stable. It shows no signs of going anywhere. And so explaining that longevity and explaining the original formation is a challenge for future observers and fluid dynamicists. So now let's take a step back and look at the remote sensing of these atmospheres. How do we actually determine what is present within the atmosphere and what's changing and what's going on? This chart compares the spectrum, and in this particular case it's Saturn, but you can think of this as being representative of all 4 of the giant planets. The spectrum all the way from the ultraviolet on the top left out to the far infrared and submillimeter on the bottom right. We can divide this spectrum into 2 regimes. The one on the left is reflected sunlight, and the one on the right is thermal emission. The latter is where we're able to deduce the temperature of the atmosphere from the spectra that we measure. Now, from the reflected sunlight perspective, what you have is photons from the sun spanning the ultraviolet out into the near infrared, traveling out to Jupiter and Saturn, where they're then reflected back from the cloud decks and the gases that we see. If this was a perfect reflector, it would be like a mirror for the solar spectrum. So you expect the shape of the reflected sunlight spectrum to be like the solar spectrum, albeit reduced over the great distances out to the Jovian and Saturnian system. But it isn't a perfect reflector. The gases that are present within the atmosphere create absorption features where they eat away at the light, meaning that far less light is then reflected back at certain wavelengths. Those absorption features are always in the same location. They're characteristic of the specific species that are present within the atmosphere. And I've labeled several of them in the diagram on the left-hand side. The most important from the perspective of reflected sunlight on the gas giants is methane. Methane does a lot of the work in absorbing solar energy in then to heat up the atmosphere of Jupiter and Saturn, but also to create this characteristic visible and near infrared spectrum. Now, visible spectrum is typically looked at with cameras, with CCDs, and spanning the 0.4 to 0.9 micron range. The near infrared is typically looked at with imaging spectrometers spanning the 1 to 5 micron range, and that's where you get an overlap between reflected sunlight and thermal emission. And then the thermal emission range is typically observed with things like Fourier transform spectrometers, mid-infrared imagers, and instruments of that kind. Now, as you go out into the thermal infrared, the influence of reflected sunlight is dying away. It becomes pretty negligible for Jupiter and Saturn. The undulating shape of the continuum that sits beneath all of the details that you see here is formed from the collisions of hydrogen and helium. We call it the collision-induced continuum. By themselves, hydrogen and helium shouldn't be interacting with the electromagnetic field. But when hydrogen and hydrogen collide, and when hydrogen and helium collide, they create instantaneous dipoles that interact with the radiation field and create this opacity which limits how far down we can see into the atmosphere. So if there was nothing else there but hydrogen and helium, these spectra would be completely smooth. And you can see a hint of that in the far infrared continuum at the bottom, in the bottom diagram. But of course, it isn't just hydrogen and helium. There are trace species present. Species that are down in the troposphere of this world create absorption features. That's because the temperature at the core of the absorption feature is lower compared to the surrounding continuum. You get a dip down within the thermal spectrum. Similarly, we have species that are present in the stratospheres of these worlds, and there the stratospheres are hotter than the background. So compared to the continuum, the stratospheric emission features stick up above the hydrogen and helium continuum. And this complicated spectrum we can use to diagnose both the temperatures and the compositions of these worlds. Let's take a little bit more of a look at the mid-infrared spectrum again. So here I'm zooming in on the 5 to 17 micron region of the spectrum. The black curve is the spectrum of Jupiter. The red curve is actually the telluric transmission. So our ability from a ground-based facility to look through our own atmosphere and detect the light from Jupiter. I'll point out a few features here. We have that hydrogen and helium continuum that we can use as a thermometer to measure the temperature of the troposphere. We have those absorption features due to volatile species, so things like ammonia and potentially hydrogen sulfide and water, which are absorbing light, but tell us about the gases that then condense to form the aerosols. The aerosols themselves then show up in the spectrum around 8 to 9 microns and 5 microns, allowing us to deduce the distribution of clouds within a planetary atmosphere. We have emission features from stratospheric chemicals, which allow us to study the chemistry. We have emission from stratospheric methane. And if you assume that methane is well mixed, then what you can do is measure the temperature using the strength of that emission feature. And then finally, throughout the spectrum, we have little absorption and emission features from disequilibrium species. These are species that shouldn't be there unless you have strong mixing of the atmosphere from deeper levels. So these are species that should be locked away at depth, but are actually present within the visible regions of the atmosphere because of that powerful mixing. And disequilibrium species is a way to trace the strength of the mixing that's taking place within the atmosphere. So if we've measured these spectra from reflected sunlight and then from thermal emission, we've taken those measurements from ground-based facilities, from space-based telescopes, and from visiting spacecraft. The way we then interpret those data is with what we call a spectral inversion, or to put it another way, we're trying to find the combination of temperature, composition, and clouds that best reproduce the spectrum that we have measured. Now, this is a degenerate problem. That means that there's not really a unique solution to it, but there are a set of solutions, a family of solutions that we can hone in on if we apply our knowledge of physics, chemistry, and cloud formation to try and remove those outlandish cases and focus in on the things that we think are physically and chemically plausible. We start by creating a spectral model. So this spectral model contains that collision-induced hydrogen-helium continuum, so the underlying opacity. It includes then the emission and absorption features from the various gases that we expect to be present. And we include the absorption and scattering properties of the aerosols that we think will be forming at different locations within the atmosphere. These are all sources of opacity which need to go into our spectral model. The next part of the spectral model needs to understand how the observations were taken. Were we just looking at a distant point of light and all the light was integrated into that single point? Or were we in orbit around the planet looking down at a specific latitude and longitude straight underneath our spacecraft? Were we perhaps looking off at the limb of the planet or monitoring a star as it was occulted by the edge of the atmosphere? All of these different geometries influence the shape of the spectrum that we're going to measure, and combined with the sources of opacity, give us our first guess at what the measured spectrum should look like. The inversion then means that you iteratively change that forward model. You might tweak the temperature, you might tweak the clouds, you might change the chemistry until you achieve a close fit to your measurements within the uncertainty on those measurements. You might still have a vast swathe of potential solutions, all doing a good job at fitting your data. And it's then a job of people doing interpretation with models of the way in which the energy is distributed through the atmosphere, or models in which dynamics are redistributing material, or chemistry is influencing production or destruction of different materials. It's down to those interpretations to figure out which of your family of potential solutions is the most realistic. So what I'm trying to get across here is that there is a challenge faced when trying to interpret the spectral data that we measure. And that challenge, we're never at the end of it. We always have more complexities that we can add to our models in order to better understand the processes that are taking place within these worlds. Just before we then start to talk about some of the detailed results that we're getting, here's a taste of some of the observations that we've been able to observe in the mid-infrared spectrum I was showing you earlier. This image of Jupiter is at 5 microns, showing clouds in silhouette against a deeper, darker background. So where you see dark colors, that's because the clouds are absorbing light. Where you see bright colors, that's because there are negligible clouds allowing emission to escape from the deeper atmosphere. For Saturn, you see a banded structure of temperature, where temperatures are changing as a function of latitude, underlying the normal fairly pale yellow appearance that you have of the planet. And in the bottom, you have Uranus and Neptune, much cruder because our capabilities from ground-based facilities are still in their infancy, but nevertheless, we're able to see the rings of Uranus, we're able to see the warm North Pole of Uranus, the bright warm equator. And for Neptune, we can even see a banded structure up in the stratosphere of this ice giant. So everything we're learning for Jupiter and Saturn, we're hoping to one day apply to similar quality data for Uranus and Neptune. We'll now move on to the fourth part of the presentation. But for now, let's take a moment to take a break, pause the video, have a think about what we've already spoken about in terms of the motivations, how we explore these worlds, and how we interpret remote sensing data. And in the next part of the presentation, we'll talk about the structure, circulation, and meteorology of Jupiter and Saturn.